meet you too.
So where are you, Mehmet?
I'm in Turkey.
Ah, you're in Turkey.
Istanbul.
Beautiful.
Yeah, thank you.
And Professor Pare?
Yes, I'm in Canada, in Halifax.
Halifax.
Yes.
Nice.
Yes. Well.
Well, it's
Yeah.
so nice.
Up until now, COVID was almost nothing here, and then over the last 2 weeks, now it is exploding. So
Really?
Yes. Yeah.
But in Canada in general, or in Halifax?
In Halifax, in Nova Scotia, it was very small. We were having 2, 3 every day, and then after that, it was 20, and then 50, 90, 150. So it's everything is closed down now. Restaurants, so the buses still run, but mostly everything is closed. So my wife does food shopping online.
Mm-hmm.
Okay, so she clicks stuff, and then you drive there, and then they put it in your car for you.
And have you been already vaccinated?
Yes, I got 1 shot.
Okay,
the
good.
Pfizer.
Good, you're on the other side then.
Yeah. So a lot of people have been vaccinated, but it's still.
Have to be careful. Have to be careful.
You have to be careful. Yes. It's.
That's it. Because if they don't do anything, then it just keeps rolling out.
Yes. Yeah.
So.
We are also in the same situation. It's complete shutdown here for about 20 days.
20 days.
Yeah, total curfew.
Yeah.
Total curfew. Wow.
Oh.
Yeah. I mean, if you go outside, then they charge you a lot of money, which is twice the minimal wage. So it's too much.
Better is to stay at home.
Is that all of Turkey, or just Istanbul?
All of Turkey. Yeah.
Oh, wow.
I mean, just last week we were leading in cases per million population. But I mean, Turkey has a relatively young country, so there is not much death, but also a lot of, elderly has been vaccinated already. But still,
Everyone has to be careful.
worrying.
Yeah.
As we see in Latin America, how beautiful it is when things are not taken into care.
Yeah.
Good. So Juan, you tell me.
Yes. Let's start. So welcome everyone to this new session.
Let me share my screen.
Yes,
Am I sharing
it?
Is it shared?
Yeah. It looks very good.
Okay, good. So Juan, you tell me when to start.
Yeah, please go ahead. Yeah, thank you very much, Bernardo, for accepting our invitation and for coming. Thank you so much. Yeah, go ahead, please.
Okay, so thank you very much for joining. And as I just said before, I'm not very good at these virtual lectures, so I'll try to do my best. So I will give a talk about this very complex title with many words together, Pontrjagin duality, multiplicative gerbes, and I will try to convey the idea of what are all these things together by building on the finite group case. So more or less, this is the plan, more or less. So I will try to tell you the idea of what happens whenever we have a finite group, which many things are more developed than in the topological group case. So I will tell you about the Drinfeld Double, a little bit about pointed fusion categories, and what is the Morita equivalence of these pointed fusion categories. And then I will show you what is the question that is has to be raised or appears on how to generalize the previous constructions to the topological group case. We could even think just of Lie groups. And for that, I will introduce a cohomology theory that is suited for studying this problem. which is, I called it Segal-Mitchison. It was written by Graham Segal in the 70s, and he says in his paper that it was joint work with Mitchison. I will explain what are multiplicative gerbes using this cohomology theory, and I will explain how in this framework one can generalize some of the results in the finite group case, and I will tell you at the end which type of somehow products or byproducts one could have. We'll finish some conclusions and many somehow questions or open things that I don't know how to answer. So let me start by somehow putting the subject into track. So we want to somehow study symmetries, and these symmetries are now somehow written in the terms of Hopf algebra, if you want to name it. And so these are our quantum groups. These are some sort of the formation of our classical groups. And we should think that our quantum groups are symmetry groups. So they generalize groups, and they're very somehow workable algebraically. So of course we have Hopf algebras, their non-commutative version and non-commutative version, and their generalizations. Generalizations are there many. I will not somehow work into them, but I just want you to see that this is where we're heading. So, and of specific importance that I want to bring in is this Yang-Baxter equation. This Yang-Baxter equation, you can see here in the little graph, is just somehow modeling how different braids somehow interact, and you can model them somehow combinatorically by saying when two braids somehow cross each other. But then when you do that, you want to see that, or to say that this graph here, you can take the braid in the middle, you can just slide it over to the right, and these two combinatorial diagrams should be the same. And this is written in this equation, which is simply telling you first braid the first two, braid the second and the third, and braid the first and the second, and should be the same as this other type of braiding. This is very important because this is a condition of integrability for one-dimensional, two-dimensional quantum systems. And whenever we think of a quantum integrable group, we think of a Hopf algebra that's somehow also endowed with this type of solution of the Yang-Baxter equation. So it has something that's called an R matrix, and an R that makes you somehow satisfy this equation. These are quasi-triangular Hopf algebras. So one main question, or one question that was raised before, is how do I cook up examples of algebras that are endowed with this R matrix? And at the time there were very few examples, but then came this very nice double construction, Doib and Drinfeld, which allowed one to construct an R matrix in a very canonical way, starting from any finite dimensional Hopf algebra. So the idea is the R matrix will be constructed by using a canonical object in this Hopf algebra here. So we take our finite dimensional Hopf algebra, we take the dual Hopf algebra with all the dual structure, the co-product, the dual, the product, the dual, the unit and the co-unit, and the inversion operator. And we construct this Hopf algebra, which is the tensor of these two Hopf algebras. But then we want to show that there is an R matrix in this Hopf algebra. So we basically need some element that has 4 entries, if you want to imagine that is the Hopf algebra, because it has to be an endomorphisms of this Drinfeld Double tensor, the Drinfeld Double. We should think that this R matrix is telling us how do we do this braiding of 2 braids between the Hopf algebra. It turns out that if you take the image of the identity map, that it lies in this H dual tensor H, and you can construct it using a basis and a dual basis, you can show that this R that is written in this way, namely, again, this is the unit, this is the element in H dual, this is an element in H, and this is the unit. If you take this matrix, if you want, or its endomorphism, it precisely satisfies the Yang-Baxter equation. So this gives a whole bunch of examples, or a whole bunch of Hopf algebras, which can be endowed with the structure of an R matrix satisfying the Yang-Baxter equation, and therefore we have a lot of somehow algebras that we can play with that solve this Yang-Baxter equation. Well, later on, let's just write down this specific example for the case of a finite group. So we take the Hopf algebra associated of the group ring, and then we take the dual of the group ring. And I just took some base. Whenever we have a letter, we have an element of the group ring, and we have a delta. That means there is an element on the functions of the group ring, which is basically the delta function. And one can simply write the whole thing. So I wrote here the product. The product here, you might think that it's already convoluted. It's a convolution product, but you can write out everything very simply. This is the unit here, so it's the unit in the one and the unit in the other, the co-product, and whatnot. So this is just basically taking the example that I just said before, applied to the group ring itself. But it turns out that this Hopf algebra, as it is here, now that is quasi-triangular because it has this R matrix that allows it to solve the Yang-Baxter equation. It could be somehow twisted, and this could be twisted whenever we have a degree 3 normalized cocycle on the group. Recall G is a finite group, and we have a 3 cocycle, and then we construct specific somehow cochains that are based on elements of the group, and we change a little bit with just simply some phases. We change the product using this cochain. But in some sense, when you make Y fixed, then this gives you some sort of a specific 2 cochain. And then we change the co-product with this other element. Of course, they all fit together. They're not just some sort of random invention. They just all fit together. And then you can just change the inversion operator. The R matrix stays itself. And what matters here is that we have somehow changed the associativity, and the associativity is now not strict, but it's almost strict. And this somehow is measuring the mistake of being non-strictly associative. So it's somehow up to homotopy associative, if you want to name it. So what we have done here is we have somehow allowed to somehow change the associativity by a non-strict associativity. And we do that because at the end, what we want is some sort of theory on which are the modules of this object, maybe tensor, you can multiply them. But at the end, you don't want this tensor product to be on the nose, somehow associative, but it could be up to isomorphism associative in some sense. So this change of the associativity by a weak one is still okay. Somehow you take isomorphism classes, you don't see that. Whenever you have the representation of this object, you don't see that. But if you don't have the isomorphism classes, but you take the actual representations, the tensor product is up to somehow isomorphism. Now, this cocycle, these letters that I just told you, beta and mu, are simply coming directly from taking G acting on itself by conjugation and taking the semi-direct product. And I want to take this simple map, which is just multiplication, and you pull back the 3 cocycle, it splits into these pieces. So these pieces that I just show you, this beta and this mu, they are somehow interconnected. They are very highly related, and that's why it makes everything happening. So I'm not going to show you how all the conditions of the quasi-triangular, quasi-Hopf algebra are satisfied, but they all fit precisely because they come from this pullback of this cycle. So this is what is called the twisted Drinfeld double of a finite group. Let me just go back to recall you what is the ingredient. The ingredient is just a group and a 3 cocycle. And with this group, G and the 3 cocycle, we construct a Hopf algebra that is now called quasi-Hopf because of the associativity that is now weak, and is moreover quasi-triangular because it satisfies the Yang-Baxter equation with this element. So we have built up a new Hopf algebra, almost associative, that satisfies the Yang-Baxter equation, that in some sense, you should think of it, is somehow satisfying the conditions of integrability of 2-dimensional quantum systems. You should think that you have some sort of 1-dimensional tubes that you can just play around in 3-dimensional space, and these R matrix tell you how do they interact with each other. Now, what are then these representations? And then you can, this is just a Hopf algebra, or a quasi-triangular, quasi-Hopf algebra. And you can find its representations in the canonical way, because you have a coproduct, then they become a tensor category, or a modular tensor category. And it turns out that in this case, because you have this R matrix, then it becomes braided, and it's not degenerate. And the point is, and the important fact is that it's somehow the information you require to define a Chern-Simons topological field theory that extends somehow. Whenever you have a finite group and an element in the cohomology, third cohomology coefficients in the circle, which you might think of it as an element on H4 of BG, that you can construct a Chern-Simons 2+1 topological quantum field theory, as it was defined by Atiyah. But in this somehow example precisely, you may not only define the field theory for dimension 3 manifold closed and 2-dimensional manifolds that on which you cut the 3-dimensional manifold, but you can go down to define the information on 1-dimensional objects. In this case, I'm going to put the circle. So that means that you can go down, and so for the manifolds, 3-dimensional manifolds, you associate a number, which is to integrate the Chern-Simons form, and it's an element that is U1 valued. And if you take the 2 dimensions, then you have some sections of a bundle. But the point is that when you go back to the circle, this is a very nice theorem, you should get a modular tensor category. And the point is that these modular tensor categories precisely, they're representations of this Drinfeld double. So if we want to do Chern-Simons theory with a finite group, and we want to somehow know what do we assign to a circle whenever we cut a manifold that is 3-dimensional into surfaces, and the surfaces may have corners, the circle gets assigned this modular tensor category. So it's a very specific somehow Hopf algebra that has all the information required for the topological field. Good. Just somehow to put it in other words, or perhaps for people that have seen it in another type of universe, these representations, you can take the isomorphism classes of them, and because it was a tensor category, and as I just said, the tensor product is not precisely associative but up to homotopy, then if you take pi naught, then it becomes an algebra. And so what is this? Well, one can do the calculations, and it's precisely whenever you have a finite group, this is what Fried Hopkins, Telemann, and others well called, or is the G twisted equivariant K theory of G. Namely, G is acting on itself by conjugation. This G on the bottom act on G by conjugation. And we choose a specific twist, that the twist should be living in the third equivariant cohomology of G with integral coefficients. And I just put a tau here, which means there is some transgression map. So it's not omega per se, but it has to be transgressed. And if one somehow opens up this into pieces, and then one just take a look at how is it as a module. As a module is just, you take this, you take conjugacy classes of elements of the group, you take the centers of those elements, and you take twisted representations, projective representations that are twisted by this beta. This beta is the same one that I just said before, and back there. Let me just see really quick. Let me go back. So you have it here, this beta. You fix your element here. You can define a 2 cocycle if this is if this G and H are just element on the centralizer. And therefore, you can define these somehow modules, or these Z modules. But the point is that you can even more, you can multiply elements in this Z module. And this, you can do it by the pull-push product structure, namely you pull things back to a place and then you pull out. Or you simply bring the ring structure that's coming from the representation of the double. So this is somehow a key point of this talk. So this is a construction, the twisted equivariant K theory of G, which can be done somehow in K-theory terms, whose product structure could be realized because somehow this twisting is multiplicative. And one can show that this as an algebra is this thing on the right hand. But as I just said, this is just isomorphism classes of an object that we had before. Now, as the motto is to work out on topological groups, this is what I would like you to somehow to think. And in the sense, okay, G was finite. But of course, we know that we have Chern-Simons theories for topological groups, for Lie groups. So what is the description of all these things whenever the group is topological or Lie? Well, this Friedhoff-Installemann theorem can be done for compact Lie groups. It's not exactly what is here on the right-hand side for topological Lie groups. This thing on the top is not well known. It's not precisely known what it is, and that's somehow the motto of the talk. So let me continue. So to get a different description, of how to get the Drinfeld double, I will go now to the world of fusion categories. Somehow fusion categories are tensor categories that are semi-simple and simple. So let me just construct a very simple type of fusion category. Perhaps the simplest fusion category is this one that is here. It's basically you take a finite group. You can have the omega, which is the 3 form or not, like the 3 cocycle, and you construct some sort of a tensor product. So what you have is G-graded vector spaces. So for every letter in the group, you put a vector space and you add the map. That's an element, that's an object. And then you put a monoidal structure, which is based on the monoidal structure of tensor of complex vector spaces. You simply tensor them. But of course, you need to do it using the convolution product of the letters of the group. And you want to think what is the associativity. And the associativity here, we use the fact that we may not do it strictly, and we just simply collect information of the associativity in some phase, and this phase satisfies a cocycle condition, which is the pentagon. Anyway, this structure is a fusion category in the sense the fusion categories are defined, and it's called pointed because all somehow simple objects are invertible. And what are the simple objects? Well, you may think that any vector space is the union, is the sum, direct sum of one-dimensional vector spaces. So you just take a one-dimensional vector space in each letter of the group, and of course it's invertible because you may take the one-dimensional vector space on the inverse letter, and using this product you get the inverse. So pointed fusion categories are just a group and a twist. And this is the simplest somehow case of fusion categories. Simple enough to produce non-trivial examples, which is what matters now. Now, but in the world of fusion categories, you should think of fusion categories some sort of categorification of an algebra. And therefore, algebras have modules. Well, these fusion categories have module categories. Now the wording becomes annoying because the modules of a fusion category are called module categories, but we should just think that it's a module. So we have a tensor category C, and of course, we just mimic the definition of what is to have a module of an algebra. And we just have, well, what is a category on which we have a functor from this product of categories, etc., etc. Of course, we need that the product of the action is associative, but its associativity is controlled. It's not strict, but it's controlled by specific somehow element on the units of the complex numbers, and of course satisfies some pentagon axioms. Now, because I have a fusion category, then I have some modules that are irreducible, decomposable, and in this particular case are just simply associated to orbit types. So a module depends on an orbit type and a trivialization of the cocycle of the group. Those are the modules, and one can take isomorphism classes and whatnot. I don't want to somehow deal in the whole module category of this, and there are morphisms about these things, and there are 2 morphisms. So of course, the modules of a tensor category become a 2 category. But let's just keep in mind this simple thing. Now, the point is that we want to some sort of carry out a construction that is known in algebra. You want to construct some sort of endomorphism category to do some sort of Morita equivalence. So if we have an indecomposable module, let's say an irreducible module over the algebra, which is not an algebra, is the fusion category, we simply called the dual as the endomorphism of this module with respect to the category. Of course, as I just said, this is a two category behind. These are endomorphisms compatible with the action, and of course they might be weak, and etc., etc. So it becomes, in this case, it becomes a one category. Now the point is that if the category itself, the module, is semi-simple, then the dual is semi-simple, and because we're working in fusion categories, which are some sort of finite dimensions, we have a double dual construction. Really, really useful here. You dualize twice, you get into the starting point. This is important. This is important because somehow we are dualizing twice to get to the same point, but each dual is not isomorphic to the original one. Good. So having said that, we also have something that is called the center, or the Drinfeld center of a monoidal category. There are many ways to define it, but perhaps the one simple way is to generalize it from the definition of an algebra. What is the center of the algebra? Well, the center of the algebra, you put an algebra, you put the opposite of the algebra, and you want endomorphism of the algebra, which are compatible with left and right multiplication. This is the center. These are somehow elements that commute with somehow both sides. So we just can generalize this to this categorical setup, and the center is just endomorphisms of the category with respect to Z and C up, namely from left and right. The point is, and this is very important in the world of fusion categories, that this already produces examples of braidings, because the center of a fusion category is always braided. So whenever you need a braiding, well, you know that you take the center of a fusion category, and already the braiding is natural because the center allows you to shift because it's precisely in the center. But the point is that if we take this fusion category that I defined before, just a group and the cocycle, very simple fusion category, and we take the center, it turns out one has to do the calculations because it's not somehow directly, one calculates and get the same things, but the center of this tensor category is precisely the representations of the double. So this is pretty useful because somehow the double construction is somehow a complex construction. It depends on the group, two copies of the group, there's a lot of information there. But by knowing this result, then all the complications somehow are in the definition of the center. So somehow everything is there in the center, but it's a very categorical construction. And somehow the group now lies itself. So this result is pretty nice because it allows us to study this Drinfeld double using this fusion category here of vector bundles over G. This is pretty good because now we could somehow use these results to see what can we say about these fusion categories. And the point is now let's try to study when these fusion categories, let me point out the specific question. When two groups with twists may have equivalent categories of modules. So namely, they define a fusion category. And I would like to know when, basically it's like a question in algebras, when two algebras will have same representations in modules, when are they Morita equivalent? And so the idea is that two fusion categories are Morita equivalent if one is isomorphic as a fusion category to the dual of the other with respect to a decomposable module. So in some sense, this simply says that C itself is Morita equivalent to the dual. But the point is that, as we know from algebras, two Morita equivalent algebras have isomorphic centers. Well, it's the same happens here in fusion categories, and it's pretty nice. If you have two Morita equivalent fusion categories, their centers are braided equivalent. But not only are equivalent as fusion categories, they're braided equivalent. And there is this very nice theorem that tells you that if two fusion categories are Morita equivalent, then, as I just said, the centers are equivalent as braided fusion categories, but the opposite is also true. This is very important, and I will tell you in a second why. That means that if the centers are isomorphic as braided fusion categories, then the original categories had to be Morita equivalent. Why do I say this? because then we are at the specific point that I wanted to reach, which is, well, if I have two fusion categories that are Morita equivalent, then their centers are isomorphic, but their centers precisely are the representations of the Drinfeld double. Therefore, if the representations of Drinfeld doubles are isomorphic as braided categories, automatically the fusion categories that we started with were Morita equivalent, and vice versa. So this basically tells us, look, if you want to somehow carry out a Chern-Simons theory in the sense of Reshetnikhin and Turayev, well, you will not distinguish these two different groups with twists because their representations of the Drinfeld doubles are isomorphic. And if they're isomorphic, they're undistinguishable as physical theories. So then one question that I tried to resolve was, when are these fusion categories Morita equivalent? What are the explicit conditions under which G and G hat with omega and omega hat are Morita equivalent? And of course, one can somehow take an automorphism of G and etc. But I just want to know when it's not an automorphism, but something more interesting. And this is a very ugly slide, but I needed to put the conditions. So the conditions of Morita equivalence is very reminiscent to T-duality, and is some sort of a T-dual construction. Nevertheless, I didn't prove it as a T-dual, but it's very reminiscent. Namely, G and G hat both are extensions of the same group K. In one, you put an abelian group, and the other one, you put its dual, its Pontrjagin dual. So where the Pontrjagin dual is precisely homomorphisms from the group A, which is abelian, to U1. So one is A, the other one is the dual. In one, you have somehow the cocycle that controls the extension F, and in the other one is called F hat. But they need to have some compatibility. The compatibility condition is that, first of all, when you do the cup product of the two, they must vanish as cohomological classes. This is this equation that I'm just highlighting now. But when you see the cocycles, or as you see it as a degree 3 forms or as 3 cocycles, they must have this explicit form. Namely, on the one side, on G, you have the extension class of the other group coupled with some information of the group of the underlying group, and vice versa. Namely, on the G hat, you have the information of the extension class of G and some information of the bottom. Namely, the class of G depends on the extension class of G hat and vice versa. And this is an if and only if. And let me just put in a little diagram because it's a little more symmetric when we put in a little diagram. So these two groups somehow are Morita equivalent, or this information, whenever they fit into this description. G is extension of K by A, G hat is extension of G of K by A hat. The extension class are F and F hat, but then they get swapped, and the twisting class of G is constructed with F hat, and the twisting class of G hat is constructed with F. So somehow the extension class of one twists the other, and the extension class of one or the other twists the one. And this is an if and only if. So this is the way that you can construct different groups and different twists whose somehow extended topological field theory 3 to 1 are equivalent. So this is somehow interesting because it allows us to change the group. Let me just give you some idea of how this works in the most and simplest example. The most and simplest example is that non-trivial. The first example appears when the size of the group is 4. So what I just did is, well, let's just calculate the cohomology classes up to automorphism on the group Z2 cross Z2, and the automorphism classes, the cohomology classes of degree 4 or degree 3 with coefficients in U1 up to automorphism. And the ones that are Morita equivalent, I put it here on the same horizontal line. So namely, if you want to know how many Morita equivalence classes are for groups of size 4, there are 7. although there are 8 possible classes. And so there are 8 possible classes up to automorphism, but there is 2 that are Morita equivalent. So it's basically saying if you want to do Chern-Simons theory with C2 cross C2 with this twist, is the same as Chern-Simons with group C4 without twist. With some students, I did the case of G equals 8. This, of course, gets more complicated as the size gets bigger. Here we have the 5 groups of size 8. And what I want to point out, these are the non-trivial Morita equivalence classes. All the others, the Morita equivalence class have only 1 orbit. But in these ones, things are mixed. And interesting is this case, no? We have the Q8, the quaternion group, no twist, is the same as D8 with this twist, which is the same as C2 to the Q with this twist. These are Morita equivalent. Namely, it's not at all so trivial to detect this Morita equivalence because the information is embedded in the cohomology class. But we may have all these interesting cases in which the group and the twist is equivalent in some sense to another group and another twist. As I just said, what's going on here is that the Q8 without twist, the twisting class of Q8 as an extension of Z2 by C2 cross Z2 is this one. It's underlined here. And I just simply, it pops out. We did also the case of PQ, similar, but somehow to tell you that there are many Morita equivalence classes going on in this game. A complete classification is of course impossible because you need to know all possible groups of a specific size and whatnot, very complicated. Now, just to finish this part of finite groups, this is something that I wasn't able to do, but two condensed matter physicists recently did, that with the information that I wrote, they managed to construct the explicit isomorphism of the doubles. Well, I had it as some result using Hop algebras, but somehow they did it explicitly. And then the isomorphism is pretty simple. It is what it has to be. It's just that one has to do it, and when I tried to do it, I did it wrong. But it is simply at the level of the algebra, and this is just isomorphism. And what is going on here, this is just Poincare duality in some sense. It is Poincare duality on the first entry and Poincare duality on the Pontrjagin duality for A in both entries. So somehow in one side we have A and the dual, and here we have the dual and A, and it's a way to swap A and A dual using Pontrjagin duality. And this somehow builds the whole isomorphism where, since everything is nicely built, symmetric, everything works out. Good, so this is the story. So the story, let me recapitulate. The Chern-Simons topological field theory extended until level 1 is equivalent for Morita equivalent fusion pointed categories. And the classification of those ones are the ones I just gave above. So this somehow brings the question, of course, many people have simply asked them, how do you try to build this same construction for topological groups, for Lie groups? So somehow there are many complications, many difficulties. Not everything that you can do with finite groups you can generalize to the continuous case. And so this is what somehow I want to pursue here. So the idea is the same. So if we have a compact connected Lie group, Reshetikhin and Turaev show that one can again do the field theory that is extended to level 1, to the one-dimensional manifolds, by assigning to the circle the fusion category of positive energy representations of the loop group, which is twisted by the level K. So namely, let me recall, if we have an element K, which is, I'm assuming here that this is the integers, of course, and K is just an integer. So this allows me to twist the loop group by a central extension of U1, gives me another group. This group, which is a central extension of the loop group, has representations, and I take the positive energy ones. And this turns out that they behave very nicely with respect to the tensor product, to the fusion product, and gives me a very nice modular tensor category. So my question or my idea or what I wanted to pursue, which is not yet resolved, is how to do the same for a topological group, for a Lie group. Namely, what is the same? Well, the same is which groups and twists may give you the same Reshetikhin-Turaev topological field theory, namely which Lie groups and twists will be Morita equivalent in some sense. But of course, the sense is not there because we don't have the language. So the idea that I took is, okay, let us extract the topological information from what we just did for finite groups, and let us try to somehow leave aside the linear algebra, say. So let's just extract the sets and the actions, and let us leave, quote, the representations aside. It's like, instead of having the group ring, let us have the group, and later we think of the group ring. So what is that we have in some sense? So these linear categories that we're thinking of in the finite case, sometimes, in some sense, we should think of now of bundles, but not circle bundles, but gerbes over sets. Now, gerbes over sets sounds a little bit awkward. It sounds very overcomplicated because all gerbes over sets are trivial. So it's like nothing. Nevertheless, if I have gerbes over sets and I take group-like objects, then it becomes interesting. The point is that this fusion category, we should think now of it as I just said, as a group object in sets, which is a group, together with somehow an extra information. So an extra information that tells me how this gerb becomes a monoid object. So this omega is simply now the information of a monoid object. And a module category in the fusion category of this sense, now it will become some sort of representation. But a representation in what sense? I will try to represent my group objects in objects where the groups act in the same category, namely a gerb. So there will be gerbes being acted by the group-like object in gerbes. A little bit of language, but the point is, the fusion category is like a group, but in a specific category, which is gerbes. And so I have a group object in gerbes, and I want this group object to act in gerbes. And this will be my module categories. So this is extracting the skeleton. And since I extracted the skeleton, I forgot about C-linearity. And then I am now in the world of topology, in some sense. I'm not C-linear anymore. So then, if I want to generalize this to topological objects, man, it's taking very long. I'll try to move forward once. Excuse me. I will try to move very fast. So, what are my categorical theories now? Gerbes. These are now U1 gerbes. I'm not going to somehow tell you the whole theory of a gerb, but you should simply think that it's just one level higher objects similar to line bundles. So instead of putting here U1, which would be a line bundle over a manifold, I put here a lifted object. So it's a U1 shifted by 1, or if you want, this is a groupoid of U1 acting on a point, and I take a groupoid extension, M as a groupoid. It's a trivial, somehow manifold seen as a groupoid, and I just take a central extension of M by this groupoid. And this is a gerb. There are many definitions of gerbs. I believe this is very simple because it looks like it's a principal bundle. Well, then we may take Morita equivalence classes of these objects. We have morphisms, two morphisms, it's a two category. It's a very rich category. You may also have a tensor product of these gerbs as line bundles. The same, you can multiply line bundles, you can multiply gerbs. And the point is that I want to mimic this, and I want to have group objects in this universe. But this description, it makes it very complicated because this description depends on the specific model one takes for P. You know, in manifolds, you take a manifold and you're supposed to have an open cover, and everything is dependent on the open cover, but then somehow the open cover disappears. But whenever we're talking about these categorical objects, the cover is always there. And it's pretty annoying to work with covers. So I just wanted to use some model on which I lose the geometry, but I win at having a specific model, simple models, but I lose the geometry. So this is where I bring this cohomology theory, and this is some sort of like a diversion, because this is a cohomology theory that is not well known, not so much used. It was somehow developed by Graham Segal, 1970, and the idea is to mimic the constructions done in the finite group case for topological groups, but in the sense that the cocycles, that the cochains which are done in group cohomology carries out very simply to the topological case, but on which the topology is taken into account and the appropriate conclusions are gotten from the cohomology theory. Namely, one can generalize in many ways group cohomology. One can take the cohomology of the classifying space, but that one somehow kills a lot of information. Example, if you have a contractible group like the reals, you take the classifying space, contractible, topologically is nothing. Nevertheless, it was a group, and as a group, it had a lot of information, because the cohomology of the reals as a group with coefficients in the reals is not trivial. So Segal somehow developed this cohomology theory to be able to have the cohomology of groups on one side, continuous cohomology of cochains, and at the same time to recall and to obtain the cohomology of the classifying space. Both things appear in this cohomology. So what is the idea? The idea is to choose or to assign, to get coefficients. Now the coefficients will be abelian groups, but topological in a specific category, compactly generally, locally contractible. A basic point is that whenever you see this fibration, it has to be a fibration of groups. So you have an abelian group. E of an abelian group is an abelian group. It's easy to construct the topological, the group structure. You take the quotient is BA. BA is also topological group. So this is just not only a fibration of topological spaces, it must be a short exact sequence of topological groups. Using that, one can resolve any topological abelian group by contractible groups, which is just simply, you simply use this thing and do it again. Namely, you have EA, which lies here. You now take BA, you take E of BA, and then this is the map that you're having here, and you have the canonical inclusion, and you keep going. And it turns out that this is a very nice resolution by contractible topological abelian groups. And the idea of Segal is, okay, once you have this, then you construct a cochain complex for any paracompact case, namely maps to this complex, and you just calculate the cohomology of that complex, and that's going to be our Segal-Mitchison cohomology. In the case in which we have a space, it's very simple because it's just giving a very simple homotopical invariant. It's just simply the homotopy types of maps from the space to the M, the suspension of A. Important to notice is that the zero level is maps, it's continuous maps. So somehow we are keeping track of, you should think that this is like a sheaf, and the zero cohomology is sections. No, it's a trivial sheaf, and this is just sections. Good. Interestingly is when you get a simplicial space. When you have a simplicial space, then you can construct the double complex. And you take the total complex, and you take the cohomology of the total complex. And this is what Segal associated to a simplicial space. And in here, things are highly more interesting because then we are mixing somehow these homotopy types of map from a space to the suspension of A, plus taking into account the structure of the group. What is important is that if we take the simplicial space associated to BG, and we define the cohomology of the group as the cohomology of the simplicial space with coefficient in this abelian group, then what is nice is that the first two cohomology groups are what you want them to be. Namely, H1 is homomorphisms, continuous homomorphisms, and H2, more importantly, is central extensions of topological groups. All the topological extensions of topological groups. And note that I didn't put any condition of compacity of G. G doesn't have to be compact, A doesn't have to be compact. They just need to have some conditions associated to principal bundles, that's all. So compactly generated, G has to be paracompact, I believe. but nothing with compacity. You can put the reals, and it works well. The point is that H3, which is this thing that we use to twist the pointed fusion category, it has been shown in some ways and different ways that H3 is extensions of G, and I put a 0 to denote that is a 2 group, but on which there are no non-trivial 1 morphisms. So it's just a 2 group in pi naught. And then I have this other 2 group, which is A, and I put it in pi 1. Namely, it's a 2 group with only 1 object, and A has morphisms. So if I want to know what are the 2 groups extensions of this G and A1, precisely are classified by this H3. So this gives us something already on the hand, which is nice. Elements in H3 are 2 groups, which are extensions of G by A shifted 1. Very nice, because this is a very explicit thing. It's a 2 group. It's not somehow, it's a very strict object. Good. Namely, so we have many things. So if G is discrete, then, or the coefficients are contractible, we get the cohomology of continuous cochains, no? The standard cohomology of a group with continuous cochains. If the coefficient is discrete, then we just recover the cohomology of the classifying space. Because if it's discrete, there is not much topology going on the map space. Importantly, we have Lindell-Hochschild spectral sequence, whose second page is the cohomology of the base group with coefficient the cohomology of the fiber. And then we can do a lot of topology. There are many other properties that are failed, that are not there, that are not proven in this cohomology theory. So it's not a complete cohomology theory, but it's very nice and it's very suited for calculations, but it's not complete in the sense of other cohomology theories, which are somehow universal in some sense. This one, not yet. So just to somehow move this thing a little further. So what are my gerbes? Well, I just take this cohomology theory, and since I want a gerbe to be classified by an element B squared of A, then this will be 2 cocycles, simply 2 cocycles. This is a gerbe. And of course, if we are in a homological model, then it's easy to construct the higher categorical extra information, because now it's homological, it's very simple. So maps, well, we need maps to map manifolds, but somehow the information of the cocycle is mapped by a cochain. And of course, the 2 morphisms are, again, an element in the 0 cochains that maps to the elements in the 1 cochain. So it's a nice 2 category. It's monoidal, simple monoidal structure. And the point is, what will be a multiplicative gerbe? Simply a monoid object in the category of Segal-Mitchison gerbes, namely a monoid M, and precisely an element in this 3rd cocycles or 3rd cohomology you want of this Segal-Mitchison cohomology. Importantly here, it looks exactly the same as in finite groups. That's the point. But it's not the same cohomology theory. It's some other theory. But it's exactly the same as in finite groups. That was the whole point. So then one can, since we have a monoid, this monoid act on objects of the same category. And one can write the whole structure. So what is a monoid? It's a gerbe over a manifold together with an action of the monoid, such that some homological conditions are satisfied, namely that the twist is trivialized by beta. This is also, you may think of it, this condition, as if we want to define a Chern-Simons invariant on a manifold. So the Chern-Simons form is a 3 form, but its derivative is not 0. Its derivative is the second Chern class if we use SUN. But if we take a principal bundle over a 3 manifold, its second Chern class vanishes for dimensions. So you should think of this omega as the second Chern class. You pull it back and it vanishes. That doesn't mean it's trivial. Somehow there is some differential form whose derivative is that, and this is the Chern-Simons form. This is what you think of the Chern-Simons form. This beta is the Chern-Simons form. So somehow, of course, it's not written in this way, but the Chern-Simons is motivating this whole theory. And so what we have here is a manifold and its associated Chern-Simons form. And if I integrate this on the manifold, If it's three-dimensional and this is the Chern-Simons, I take the Chern-Simons invariant associated to the manifold. Anyway, so these are objects, morphisms. You can make it into two categories, and I just simply mimic my construction from before. I take a module. This is a space with a gerb. I take a monoid in gerbes, and I just take endomorphisms in this category. It turns out that this becomes a very nice cross module, or a two group, but I just wrote it in the terminology of cross modules, namely, this is a group, this is another group, this is a morphism, and there is some conditions that define that it's a cross module, or as is the same, it's a two group. The kernel gives you the pi1. This is just invariant maps. And the co-kernel gives you the base final group. And the thing is that the structure of the group on the bottom is a very nice one, which on here is an H1. Good. Let me just continue on explaining what do I need to do this Pontrjagin duality. The Pontrjagin duality, I have a group, which is a multiplicative gerb, or a monoid object. This alpha is omega, no? This is the same omega. I need a subgroup that is abelian. Why? So that the double dual is itself. This is the Pontrjagin duality. Then I needed the restriction to the cohomology of the subgroup is 0. Why? Because this is the only way for it to be a representation. Then I need it to be normal. Why? Because I need that a specific homomorphism is precisely K. And then I need a specific object in the spectral sequence. Why? Because I need a specific condition on surjectivity. If those conditions are satisfied, then it turns out, quite interestingly, that the dual, or the Pontrjagin dual of a multiplicative gerb with respect to specific module is also a multiplicative gerb, but it looks here as a two group, which fibers over a group. This is a topological group, and the fiber, now I use a different notation, is U1 shifted 1, and the dual group is an extension of the dual abelian group S. That's why it's called Pontrjagin duality, and it has a specific class. But let me show you that the diagram is the same as before. It's just the same. We just mimicked the construction for inner groups, and you can see some examples. Of course, there are gazillion examples, of course, but you can just cook up some non-trivial examples. And I cook up, of course, why it's called Pontrjagin duality, because if we start with a local compact abelian group and no twist, and we perform the whole construction, we get the Pontrjagin dual group. If you do again, you go back. Now, this is a very simple example on which we have something concrete. You may take SU2 on one side, and you may take a multiple of 4 of the second term class. This is Morita equivalent to a group which is similar to SU2, of course, SO3 cross Z2. It's not the same group, but it's quite similar. But now the twist class is the Pontrjagin class, plus some specific class that controls the way you can cook up SO3 with SO2 to cook up SU2. So these two groups and twists are Pontrjagin dual. I will not call them Morita equivalent because the theory fails. I don't know how to define that. But the point is that these two are compact Lie groups. Of course, one is not connected, but that's okay. The point is that these ones will give me equivalent Chern-Simon theories. I still need to prove that, and here is an example of non-compact groups. You may take this Heisenberg group of upper diagonal matrices with a specific twist, and then R3 twisted is Morita equivalent, is Pontrjagin dual to this Heisenberg group. There are many more. Just wanted to show you some finite groups, some compact case, some non-compact case, and many more, of course. But just somehow to finishing. So what we did, we have two different multiplicative gerbes. We strictify them in a specific two groups. This is a very strict object. It's a gigantic thing, but it's a very simple and a strict construction. Then we can carry out the center construction, which exists for any monoidal category. And the point is we show that these dual groups, namely these two, but we have to write them as two groups, their centers are equivalent. And these gadgets here, some sort comes with a braiding, of course, because they're at the center. And so what we have is that these two different multiplicative gerbes are, its centers in some categorical sense are equivalent. And that somehow, just to start finishing, we'll get to the point on which we haven't done. So let me conclude. So what we did is we did some construction on multiplicative gerbes. This construction is also called electric magnetic duality. Namely, we take some sort of some coordinates that are abelian, and we do Fourier transform. So we exchange electric to magnetic and vice versa. This is what we did with the group. This is what we did in the finite group case. And in the finite group case, we were able to show that this duality somehow forced an isomorphism of twist and Drinfeld doubles, hence giving me equivalent Chern-Simons topological field theories. Now, in the case of a topological group, we have somewhat of a different framework. The different framework is that we have a multiplicative gerbe, and we can get its center, and we know that Pontrjagin dual multiplicative gerbes will have equivalent centers. What we don't still have is we still don't have this part here, representations. So we still need to find a way to represent these centers of these multiplicative gerbes in order to show, or sorry, if we could represent them, we expect, the way I put here, we expect that we will get precisely the Fried-Hopkins-Telemans construction for any compact Lie group. And if we are able to show this on the first box, then it will come automatically, because of the centers, that if we have Pontrjagin dual multiplicative gerbes, then their twisted equivariant K theories are isomorphic, and therefore their Fried-Hopkins-Telemans, the Reshetikhin-Turaev topological field theory would be equivalent. But as I said, we still don't know how to bring this world rep in here, because we still don't know how exactly are we going to represent these two groups. But it should, I suppose, for the people that know about this, perhaps there is a very simple way to do it. We have a very simple two group, and we would like to get some sort of a linear object out of it. And so it should not be difficult. I don't know how to do it, and automatically this will become. So the conclusion is that we don't have this part, but we believe this is very close to have it, and then this would somehow give an idea of what is that one could somehow endow to a Chern-Simons theory to a point, namely the multiplicative gerbe, although it's not a fission category, but because we were able to get out of the world of fission categories, to extract the skeleton, to work with the skeleton on the topological case, we were able to put a little bit further the question, although we still don't know how to represent them. So this is the work with my colleague Konrad Waldof and my student Jaider Blanco, and some other works that I did on finite groups. Thank you very much. Thank you.
Thank you for the great talk, Bernardo. It was great. It was pretty great. Thank you.
Great. Yeah.
Yeah. Are there any questions or comments for Bernardo? Well, Carlos has a question, so please, Carlos, go ahead.
Yeah, thank you, Bernardo. It was very nice. I think it's the second time I hear you about this term. Yeah, the first time was when was your student Blanco. I don't know where. But, I have only two questions. That when you about this the Reshetikhin-Turaev theory. Well, at first, so it is topological. So it's similar of this work of Crane and Jeter when they work with these fat surfaces and with corners, and they extract some implicit structures of TQT, for a 1 + 2 + 3,
Exactly. So it's topological, and it's 1, 2 + 3, because it's a Chern-Simons. It's a Chern-Simons theory.
Yeah, it's just not, but also you talk about that you take the P0 and you have this result of Fred and coupling that you choose some orbifolding. So you choose the orbifold part, and so it says that it's an equivariant theory. Yeah, and also you are choosing the center of Becht. So I think you have an equivariant and open theory. Yeah.
Well, Carlos, to tell you the truth, I don't know much about it, but the thing is, the reciprocal Uribe tells you what to assign to the circle, and the circle is there's a theorem that it has to be a modular tensor category, and generic. Now, in whenever you have this Drinfeld double, you precisely the center, or this Drinfeld double, it is a modular tensor category. And so in some sense, it fits well, and this was shown by Fried, that precisely everything that you need works, and when you get to the circle is the representation of the Drinfeld double. Now, you haven't gone to the point. Somehow you stop at one-dimensional. It's not a fully extended. You may fully extend it if you assign to a point the fusion category vect G omega. Okay, that's another theorem that's by Turaev. No, but that's by I don't know, Enriquez. Many people read themselves. But you don't need to do it. That's the whole point. You don't need to go to all the way to the point. And one way to understand it is because if you go all the way to the point, the modular tensor category that you're interested with, which is what is on the circle, you may assign two different things to the point, and you may get the same thing on the circle because it's the center. So this is somehow some sort of a byproduct, which is telling you, well, you don't need to go all the way to the point, because by the theorem of Ostrich, if you know the center, if you know that your modular tensor category is the center of a tensor category, somehow the tensor category is inside the center. So, but the thing is, you cannot recover the category. You recover only the Morita equivalence class of the modular tensor or the category. It's like having the center of an algebra. You don't recover the algebra, or the Cauchy homology of the algebra. You just recover the Morita equivalence class of the algebra, because Morita equivalent algebras have equivalent isomorphic homological Cauchy homology. So in some sense, it's telling me, look, okay, so that means that my theory somehow is not sensible to changing the group and the cocycle per se, because it's sensible only to the center. So then these things, but it makes sense if you think algebraically as algebras. What is that you want to know about algebras? It's representations. So you're not so much interested of the algebra per se. Of course, you use it to calculate, but you want all the Morita equivalence class of the algebra. So many constructions depends on the Morita equivalence class of the algebra. So for the case of the compact Lie group is the classical case of Chern-Simon's theory that Witten did to assign invariants of knots. Somehow it's known that what goes for the circle is this Berlin algebra, which is the algebra associated to the positive energy presented with all these things. And one could ask if it's important to go to the point. So one question that is over there is 7 years around. What goes on the point? Well, it depends. It's difficult because it's not clear what should be on the point. But somehow my approach, or what I did, is to get out from the universe of complex linear categories and to extract the topological, the geometrical structure, and not so much its linearization or its representation. But of course, when you do the algebra, you do the physics, quote, you do the representations. You don't see the groups. You see only the algebra of the representations. You don't see the groups per se. So somehow one has to construct a representation category in some method. Of course, if you see what is Hopkins elements Fried, it's twisted equivariant vector bundles. In some sense, those are representations that are moves around equivariantly. No? that's precisely what you were asking me. How what is the relation, to ask me, of the Friedhoff-Hopkins element? Or
No, it's a confusion because and then the Chern-Simon is 0 plus 1 plus 2. Yeah, and what I was I thought that was 1 plus 2 plus 3. That is some case studied by Crane. Yeah.
Oh, you see, these are complex things, and perhaps anybody can correct me.
Yeah,
I just always think the most simple way for Chern-Simon. Chern-Simon is a degree 3 form that is integrated on a 3-dimensional manifold, therefore has to go all the way to 3. Now, if we put it 2 plus 1 or 2, or I don't know, it's a very confusing terminology. But
that's something to the point, no? I said that's the.
Yeah, if you want to make it fully extended, you want to go down all to 0-dimensional manifolds.
Yeah. Yes. And just one, I don't know if it is possible, but if you are, your generalization is for Lie groups, it is possible that you could make the Chern-Simons of this, well, these theories for groupoids, also for orbifolds, and you can say similar like, well, if the TQFT are equivalent, then what say about the orbifolds?
And somehow what is going on here, in some sense, from my perspective, how I see it, is that we do have some symmetry, the real symmetry. It's a group at the end. It's a real symmetry of the physical system that is appearing whenever you have, let's go to physics, whenever you have the eigenstates of your Hamiltonian. These eigenstates of the Hamiltonian, from these eigenstates you may construct connections. And these connections, in the appropriate case, if you are coming from an SUN bundle, you can associate to these connections invariants that are precisely from Chern-Simons invariant. So you're getting topological information associated to your physical states. But you see, I'm trying to answer your question by somehow telling you where this comes. So you come from a symmetry of your system, so a gauge symmetry is there, which is the symmetry of the states. And there you make a connection, you take the Chern-Simons, you integrate, you get an invariant. Now you ask me how to, it is possible to generalize this to a orbifold. And then I have to go back and say, okay, now I need my gauge symmetry to be an orbifold, which I don't know how to make sense of that. My gauge symmetry of the physics. So I don't know what that means. So then I perhaps generalize it by not thinking physically, but I don't know how to make it. Again, another thing, these are group objects, Carlos. Real group objects satisfying, and an orbifold is not a group object in anything. It is one step behind. You have a Hopf algebra with a product and a coproduct, the orbifold gives you just one. You still lack the other one, which is not bad. I'm just saying that I don't see how to make it into the game. We need coproduct and product structures together.
Okay. Okay, I see.
Well, my talk was not clear. Someone just says too many things. It's so difficult to explain these higher categorical things.
Yeah, I thought it was very nice. I really liked it.
This subject, it is terrible for talks.
Well,
I was reading this paper of Danfried about Chern-Simon theories, and he says in some place that there is the categorical number of each person has a categorical number, and it's an integer, and is the highest number on which a person can think on n categories without destroying its head. So he says he can go on to only to level 1.
To level 1.
So one category, and I think well, level 1 for me too, because you're just thinking of 2 categories.
Yeah. I think
one uses them. Yeah,
well,
one.
So I do. So for me, I think I think my level is 2. I think, but my level in co-cycles and formulas and I don't know, that might be 0. So yeah, it's the first time. So it's the first time I've seen this, and I liked it very much. But
So Juan, good point. I'm older now. I didn't used to put formulas, but lately I've been working with physicists, and I've been working and reading.
They do love the formulas.
and sometimes the formulas tell you a lot. Sometimes the formula is the answer. Yeah. You see the formula and oh man, the formula has everything there.
Yeah, you somehow try to say things, a lot of things around the formula, and it's just there. And if you're used to it, just read it, and you don't really have to say much. But so I might have very, very stupid questions. I hope that's.
Please, these are the best.
Well, one very, very basic question is, so the extension 321, this is only because it's Chern-Simons, right? Or are there any other Reshetkin-Turaev models of, I don't know, something that is not a twisted?
Well, yeah, of course. Well, in some sense, you know, any 3-to-1 topological field theory doesn't have to be of Chern-Simons type.
Yeah.
As long as you construct a 3-to-1 functor, you may cook it differently. I wouldn't be able to tell you examples. No?
Okay.
This is the same type of when do you solve the Yang-Baxter equation? Well, impossible. But let's look Drinfeld Double, gazillion of examples. The same. Give me a 3-to-1 theory. Okay, Chern-Simons. I don't have any other one.
Okay. That's a very good answer. So So the way to cook up examples is this. So that was my question, I think. So and well, the other question I think is, so I'm not. Yeah, what is this? Could you explain a little bit more about the problem of defining representations for centers of multiplicative Gerbes and Gerbes?
Yes. So, well, we have a 2 group.
Yeah.
And let's just think the group consists of a group. Well, it's an extension of a group, topological group. You may think is SU2.
Yeah.
And on the other side, you have U1 shifted by 1. And you have something in the middle, gigantic. That's a 2 group. Question: how do we construct a mathematical construction that to this functor or whatever to somewhere will give you linear representations?
Okay.
And of course, we might think that it has to be related to vector bundles, to K-theory. They have to be there. They have to be bundles over the group and whatnot. How? Because now we have a 2 group. So of course, there are people that have done 2 representations, but they are not good enough. They are not the ones that work.
Yeah.
They have, so there has to be some other thing. And I don't know the answer that somehow solves it.
Okay.
But the thing is now, if you take now the center, which is another categorical blah, blah, but similar, some sort of a similar. One would like some sort of construction that mimics what is a vector bundle. So of course I was thinking the other day we should put Fredholm bundles and twist it and blah blah blah, and I got very confused because you have to put a lot of structure into this target. It has to be monoidal, has to be 2 group.
Yeah.
and I just got confused. I didn't know what to put. Yeah.
And also you want the Fried-Hopkins element, of course. I mean, you said you expected it, but I suppose that's, you want to define your representations to get this and to get Morita equivalence.
Yeah, because
to
you see,
duality.
it's going around one, because
Yeah.
Witt-Hopkins-Telemann showed that what they constructed is isomorphic to the Berlin algebra.
Yeah.
Of course, what I want is the Berlin algebra.
Yeah.
But the Berlin algebra is based on the loop group.
Yeah.
And I don't have loop groups anywhere.
Yeah. No.
So what I do have is the gerb where it comes.
Yeah.
And so the construction of Witt-Hopkins is not at the level of loop groups.
Yeah.
And so that's why I think is the appropriate target.
Yeah.
Because unless one takes these two group and does some looping, I don't know. No, I don't think so.
Okay. So the usual theory of representations, or two representations, or let's say this bias, Neukel, and all those people that did higher algebra things, they fall short. You need to have
what I know is that the first somehow candidate that they took, that they called two representations, are bad, but because what goes at the one morphisms is always discrete. It's always the symmetric group.
Yeah.
And I don't want to have the symmetric group there. I want to have UN.
Yeah.
But not UN, because it has to be abelian. I want to have the center of the unitary operators on a Hilbert space. So the circle. So and if it's discrete, it's not the appropriate one.
Yeah.
And I suppose, I don't know, but to my knowledge, this is not constructed yet. I wish there is like a specific two category with that structure, because then K theory is there.
Yeah. Okay. Yeah, I think I understand.
Yeah, but it's perhaps it's already there, and I don't know. You see, these times of coronavirus, don't know anything anymore. Perfect. Then one.
Yeah, I think that's all my questions. I think. I don't know, Akif, do you have some questions?
Not much, but I mean, I just wonder if there is any kind of algebraic K theory involved in this.
You see, this is a good question.
So
far, no, but I was thinking the other day, just like 2 days ago,
about
preparing this
Morita
talk,
equivalence
that
detecting.
No, because you see, it's some Morita equivalence, but not of C-star algebras, because this is a Morita equivalence of Hopf algebras.
Yeah, sure, but I mean that some other kind of algebraic K theory there. You know, there are some.
No, but you're right. I
think
believe all that I did should be possible to construct in the world of C-star algebras, and perhaps there what I want to accomplish is easier, because automatically you put as you said, you do the K naught or whatever, the algebraic K theory, the C-star algebra, and it's automatic. You don't have to worry so much. And then but then we will have to construct everything at the level of C-star algebras, and I don't know how to do it because I'm not expert in C-star algebras, but I believe that's the appropriate way to do it, using Kasparov K theory. But I just don't know how to incorporate multiplicative. Perhaps it's very easy, and perhaps if you know about it, perhaps you can do it very quickly, because the whole structure is there. But I don't know.
Oh, thanks. I thought that, I mean, it might be a very irrelevant question, but
no. I believe that somehow the C-star algebras is more appropriate for this type of questions than doing it topologically. I completely agree, but somehow I'm not an expert in that, so with C-star algebras, I'm always afraid that I do something wrong.
There is variants of algebraic bivariant K theory for ordinary algebras, and
exactly, that's the bivariant K theory is the one that one needs to use here. But then one would have to write all this in language of operators, appropriate operators, and all the topology, of course, goes very well, but one has to write it well, and then it will perhaps be smoother.
I see.
But I don't do it not because I can't, because I don't know. So Perfect. Juan.
Oh, thank you
Carlos
very
and Mehmet,
much.
thank you for the invitation.
Thank you very much for coming, Bernardo.
Thank you for the
It's very nice to see you all three. Mehmet, nice to meet you. I hadn't met you. And Juan.
Nice to meet you too.
Nice to meet you.
Yeah, it's very nice to meet you. It was great having you, Bernardo. And
Very nice initiative,
yeah.
one that you've done.
Yeah, thank you.
Maybe one last thing, this about this gerbes. I'm not familiar with that, but is there any geometric relations with gerbes?
Yes,
does it
yes,
say
Mehmet.
anything
So
about
gerbes.
smooth structure of a manifold, for example?
Exactly, exactly. So gerbes originally come from manifolds and connections, and so you may put all the geometry on gerbes as in a line bond connections and connection and curvature, which is the tree form. And of course, this is what it was used in physics to do B fields and integrate over them. The difficulty, if you do it at the level of manifolds, is that just to define a gerbe with manifolds, in my point of view, if you see the definitions, it's a nightmare because it depends on an open cover. And,
I tried to read some definitions, but yeah, I agree with you.
Yeah, because it is as trying to understand the manifold from an open cover, but keeping the open cover all the time. You have the open cover. And so you have a map from manifolds. Oh, you have to have open cover and an open cover and a simplification decomposition, a nightmare. But this is just to define a morphism between gerbes. But if you kill the geometry and you make it topological, then you forget about this open covers crap and you use other type of resolutions, which are topological spaces.
Yeah.
Somehow the price to pay is that you change the simplicial decomposition by its resolution in some sense, and then you have a space. You make you take the classifying space of the simplicial space if you want. You make a classifying space, and so it's a space now. Of course, it's built out of the pieces, but you will lose the geometry. But you have a space instead of an open cover with maps, with the pentagon and blah 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 and gazillion things. And in the topological case, you see that one can strictify. Of course, you enlarge it to a gigantic thing, but then it's strict. If you leave it at the level of geometrical gerbes, nothing is strict. Everything's, of course, categorically is the same. But if you want to work with objects, it's a nightmare. It's a nightmare.
Okay.
And so that's why I didn't do the geometry. So precisely, it's a model on which you lose the geometry, but you can move forward a lot faster.
Yeah.
One simple question is, which is the following. Imagine you have a manifold as an open cover, and I want you to define the space map from a manifold to another. You want to find a map from a manifold to another using open covers, but not only that, I want you to give you a topology. If you think of it, of course one can do it, of course, but it's a nightmare because you need to define how is a little perturbation and you perturb here and what is a closed open compact, but how in this other terminology, since our solid topological spaces, it's easy to construct the mapping space, and it's just compact open topology, compact open.
Yeah.
And so you lose, but you win. Somehow it's like changing the resolution.
Yeah.
Thank you.
No. Very good question. Very good question. Man, you're streaming this somewhere that nobody's going to watch, which is very nice.
No, the way
Well, thank you very much for the invitation. But you see, I need to go home because here in Germany there is curfew.
Yeah.
In half an hour. So.
Yeah. Well, thank you so much, Bernardo. It was great meeting you, and it was great having you.
I was meeting you.
Amazing talks.
Keep healthy.
Yeah, you too.
Coronavirus is a disaster. It's killing people.
Yes. Hopefully, we can meet in person soon.
Oh yeah, Carl, you guys have a lot of money in Mexico. You invite us. I'm always happy to go to Mexico. You know that. Any conference in Mexico, I'm there. So I don't care where, Oaxaca, Morelia, I don't care.
Tamaulipas,
Better when it's Puerto Escondido.
Acapulco.
Those I like
so
better.
hopefully soon we can organize something. And
Good.
also, yeah. Okay.
Juan, Carlos, ciao. Mehmet, was nice seeing you.
See you guys.
Goodbye.
Thank you very much. See you.
No, thanks to you.
Bye.
Bye.
Well,
Bueno.